Hello everyone. So let me see. So just a heads up, yesterday I was only seeing some of the live comments. I wasn't seeing all of the live comments. So if I miss yours, I probably need to tinker with the settings a bit. But if I miss your comment, I might just have to get back to it after the video. What we were discussing yesterday was temperature, and today, and we're continuing our discussion of this equation here at the top, the first law of thermodynamics. So we're continuing that discussion, and we're kind of breaking this down piece by piece. So we started here with temperature, and then now we're moving to the entropy piece of this equation. Now I wrote out the definitions of entropy here. These two equations here, the S's, so this is like a curly S, or a cursive S, and then this is like a capital S. So these are our two definitions of what entropy is. And it's going to take a minute to kind of explain like the intuition of what that means. So the script S, this is the Shannon entropy, and then the capital S here, this is the thermodynamic entropy. And you'll notice that the two equations are pretty much the same, except with the Shannon entropy here, you have a base 2 logarithm. These are probabilities, and I'm going to have to break this down of exactly what it means. And then here we have a base natural logarithm, base E, and then we also have a Boltzmann's constant here. Now the Boltzmann constant is basically being used to put us into thermodynamic units. So that's why this is the thermodynamic entropy that you see in this equation here. And then this, the Shannon entropy, it's basically measuring the exact same thing, except you're in numbered units as opposed to, like this would be in joules. Like if you're using it to measure energy in joules, then you would need a Boltzmann constant, and then here, with the base 2 logarithm, you're actually measuring it in bits. So, like, for example, like if you download like a meme or something, and you'll notice that it takes up like, you know, a certain number of kilobits or kilobytes. So you'll notice that the image is stored as data in a number, so you have a number of kilobytes, right? So basically, those are units of bits that are stored in your computer. So that has a certain amount of Shannon information that goes with the meme, right? So I'm sure you've downloaded memes and you see how much space the meme takes up. And the amount of space, it depends on the resolution of the image, right? How big the image is, like the dimensions of the image, and it depends on like how many pixels per inch is stored in the image, right? So the Shannon information sort of like keeps track of like how many bits of information is being stored there. So so when you're using like a digital system, like a computer, all of the transistors are in binary. So the transistors are like gates, and basically the gate can be turned on or off, and the computer can control if that gate is turned on or off, right? So one on or off switch, it can be either a 1 or a 0. So So a bit that's not programmed has 1 bit of entropy, right? Because you don't know if it's a 1 or a 0, so it has a bit of entropy. Now if you know that it's a 1, or if you know that it's a 0, then you have 1 bit of information. So you can kind of see how entropy and information are related, in the sense that the information is the entropy that you do know, right? And then if it's stored as entropy, then it's the information that you don't have. So if you encrypt something, basically you're like, with like RSA encryption, you take two really huge prime numbers, you multiply those numbers together, and when you do a multiplication in the computer, that algorithm is pretty fast, right? So if you write a multiplication circuit, one direction is super quick, but if you try to reverse that multiplication, that algorithm is not simple. It's actually complicated, and usually you have to check the prime numbers, like using a brute force algorithm. So to actually reverse an RSA encryption, usually you would go through and you would just like check a bunch of multiplication circuits, and then you would keep going until you get lucky and you match the multiplication circuit that reverses the encryption, and then that's how you decrypt RSA, is by factoring multiplication. Now this is basically just an example of how the Shannon entropy would apply to like a classical computer, and this is the kind of thing that you do every day. So when you send like an encrypted website, if you don't have the public key, well, everyone has the public key, but if you don't have the private key, then you can't read it. It just comes through as a multiplied number. But if you don't have the prime numbers, then you can't read the text file, right? So that's an example of how Shannon's entropy is used, and you end up using this every day that you're on the internet. You're using Shannon's entropy, and the amount of entropy that an encryption has basically makes it uncrackable. So reversing a large enough multiplication, doing it brute force, basically it's unhackable unless you get like extremely lucky, right? That's if you use brute force. And what I want to talk about in future videos is how you can use quantum bits to reverse RSA encryption, and you can do that in seconds, as opposed to like millions of years of computation time. You can use a quantum decryption. It would take like 10 seconds, but you need a certain number of in quantum computing we measure the entropy in qubits instead of bits. So that's basically like quantum bits, right? So you would need some like megaqube bytes to break RSA. So right now, the quantum computers at D-Wave and Google, they're just not strong enough to break RSA yet. But once they get up to like the megaqube bytes level, then the quantum computers can easily break standard encryption, and we'll have to completely rewrite the book on encryption in order to keep your bank accounts from getting hacked. Basically like all of the data that's out there that's encrypted would become instantly hackable if you had a strong enough quantum computer. Now I got a little sidetracked from what I was originally talking about. So I was talking about entropy, and then so we had a little segue into encryption, and now encryption is where the information physics crosses over from thermodynamics into the digital, right? So this is a point that I want to keep emphasizing throughout this series on emergent gravity, because in emergent gravity, remember, we're talking about how the information physics is essentially generating the gravitational field. So yesterday we talked about temperature and how the temperature is essentially driving gravitation. So we really need to have like a good intuition of what entropy actually is. So that's like the information theory side of the entropy, right? So we're talking about breaking encryption, entropy, storing means. We're talking about information, right? So if you know what the bits are in the text file, that's information. If you don't know what the bits are, like as in factoring a number, that you don't have the information about what the primes are, that would be entropy. So you can see, one point that I want to make super clear is that information and entropy, they're sort of opposite, but they're related. Okay, so now that's the information side of it, the information physics. So now I want to bring it back over into thermodynamics. So now in this equation, for the entropies, whoops, those are the two S's here. For the entropies, you'll see this omega, capital omega here. Let me just get my pen so I can point to it. Right here, the capital omega, that symbol is representing the number of microstates in your thermodynamic system. Now, what does that mean? If you're using the example of, like, let's say a gas in a box, okay, and then you can imagine that the molecules of the gas, they're moving around in the box, right? So basically what you can ask is, well, if I have a certain amount of energy, how many different configurations, like positions and momenta, and, you know, I consider spin to be, like, electron spin to be a part of the entropy. Now that's going to make it a hell of a lot more complicated, but I would also include electron spin as part of the entropy. But if you want to keep it simple, we have positions and speeds of the gas particles in the box, and all of the different potential configurations of these molecules give you the total number of possible microstate configurations. Now that total number, capital omega, that total number of microstate configurations gives you a microcanonical ensemble. Okay? And now this is where things get weird. So, like, that would be like the classical picture of what's going on here with these gas molecules. So you can imagine, if you think of it all in terms of kinetic energy, you can get a lot of intuition about what entropy means if you think of these molecules in terms of kinetic energies. Now, position is the position of the molecules in 3D is also important. Why is that? Because if you're using the kinetic energy of the molecules to apply pressure by bumping up against something like a piston in an engine, so if the kinetic energy is moving these molecules, it only feels the kinetic energy from the collisions of the molecules that are near the piston, right? It doesn't feel all of them, right? So I hope I'm making sense. I'm not seeing any comments yet, and yesterday I wasn't receiving all of the comments. I was only receiving some of the comments. So I hope I'm making sense so far. And actually, maybe if I, let's see, where is my phone? If you're on my Facebook friend list, why don't I turn the ringer on for now? That way you can actually message me your question. If you put it as a comment and I don't see it, then go ahead and message me your question, and then hopefully it will ring on my phone. So that's a good way. That's how we can kind of get around this glitch, I guess. So yeah, so go ahead and message me. So where was I? Okay, yeah. So in the engine, you're combusting the liquid fuel, and when you're burning that fuel, it changes it into gas. And what happens when you change the state from liquid to gas? Well, the molecules are kind of moving around faster, right? So what's happening when you change that state using combustion? Before the molecules are kind of like not really moving as fast in the liquid state, and then when you put the heat, oh yeah, and then that ties back to what we started talking about yesterday. So that's this equation here, dq equals tds. So basically you're putting heat energy in, you're combusting the fuel, and then that energy that you're putting into the molecules changes into kinetic energy of the molecules, and then it changes state into gas, and then if you put enough energy in, then the molecules are moving really quickly, and so they'll have more kinetic energy to hit into the pistons, and then when it hits, it's almost like you're playing pool with the molecules, right? And then it collides with the piston. It bounces off. So then all of that energy from the bounce gets translated into kinetic energy that goes into the piston. And then when that kinetic energy goes into the piston, then it moves the piston, and that is how the heat energy gets converted into physical mechanical work. Mechanical work, i.e. the pressure moves the piston physically, right? So you're changing heat into work. Let me check my messages. I just got a ding. Okay, that was not related. I might have to turn this off if all the messages are not related. Okay, so I hope I'm making sense so far. So that would be another example in the first law equation that we've been discussing. This is how it converts the heat here. This is temperature times change in entropy. And as that entropy changes, then you can convert that entropy. You can convert the entropy into pressure, and then the pressure moves the piston, which changes the volume of the container. Right? The volume of the cylinder is changing from the pressure of the gas. The pressure of the gas pushes up against the piston, and then by moving this piston around, then you can convert that energy into changing the kinetic energy of your vehicle, right? So you're converting basically, if you want to look at it as like a black box, you put the fuel into your car, and then you're converting that energy of the fuel into kinetic energy on your vehicle, and that's how you move around. And that's just the basics of like combustion engines, right? if you want to just look at it as like a really simple, like fuel goes in, kinetic energy, speed comes out, right? And that's combustion. Okay, so how does this tie into information? Well, the liquid fuel has more information than the gas fuel. Or when the fuel changes into gas, you're losing information. So you can think of information as fuel. When it gets erased, then you can change that information that you know about the fuel, because the liquid has more information than gas, right? And you can change that information into energy in the form of work, and the work changes into you can use the work to change kinetic energy on something else, right? Like a vehicle. Now, one of the things that I want you to read up on, and I'm pretty sure you can do this with any kind of math background, is Maxwell's demon. So, no, it sounds scary, but it's not that scary. It's like an example, right, of how information about the thermodynamic system, if you have information about the system, then you can convert that information, which is knowledge about the system, you can convert the information into work. So, Ariel said something. So if you have more pistons, then you can do work basically like times 8 amount of work per piston, right? And then a V6 would have 6 pistons, so you're doing times 6 amount of work. Like, more cylinders means you can do work, you can perform the work faster, right? But you're also burning 8 cylinders worth of fuel to do that work, and then with the 6 cylinder you're burning 6 cylinders worth of fuel, right? Does that make sense? Yeah, thanks, Ariel. So the Maxwell's demon is basically like a demon, right? So and the demon has information about the thermodynamic system. What does that mean? The demon knows which microstate you're in. Alright, so if you remember when we were talking about microstates, a Maxwell's demon can look at the system, and he has knowledge about which microstate you're in. And if he knows which microstate you're in, then he can decide where to put the piston, because like which side of the container has more molecules. And if he knows that, then he can decide where to put the piston, and then he can extract work, because the molecules are going to spread out and push on the piston. And then when the molecules spread out, he can extract work from the knowledge of the system. So that's if you know which microstate you're in, right? Now with liquid, still don't know which microstate you're in, but you have more information about those microstates than with the gas, right? So when you convert the liquid into gas, you're losing information. Now you don't have to have a complete microstate to extract information and convert that into work. Okay. So I want you to research Maxwell's demon, and that will give you a really good idea of how I'm using the thermodynamic entropy as interchangeable with the Shannon information entropy. I'm treating them as interchangeable. Oh yeah, I was going to talk about phases, but I might save that for the... Yeah, thank you, Jessica. I was thinking of saving phases for the qubits lecture. I might be down to do that next, especially if people are interested. So with quantum states, you can have relative phases, and that's where the imaginary numbers and complex numbers, that's another thing that you can look into if you're at the algebra math level, especially to get ahead. You can look into imaginary and complex numbers. Now, it's imaginary when they first realized that you can take square roots of negative numbers, because it's imaginary, right? So, like, you can't take square roots of negative numbers. That's what they teach you in grade school. But it turns out, actually, you kind of can do that. And because there's a physics model that uses complex numbers to model a physical phenomenon, that makes it, in a sense, like a physical thing. So even though the numbers that you're using are imaginary, that doesn't mean that the concept doesn't have a physical meaning or application. So when it comes to phases, we keep track of phases using complex numbers, and if your math is maybe pre-calc level, you can look into Euler's theorem, which should have, I can write it down. Okay, E cosine phi plus I sine phi. Okay, so you'll also notice that the logarithm that we use in thermodynamics is base E. So and here with the complex waves, we have an I for the imaginary number. So here the phi symbol, that's your phase. And so if you have this complex number exponential, the EI phi, that would be how we keep track of phase in quantum mechanics, and and electrodynamics as well. So and electrodynamics is pretty classical, I would say. And so here, cosine phi, you have that's the real number part of the wave, and then you also have an imaginary part of the wave with the sine of that phase, right? I sine phi, that's the imaginary part of the phase. And then when you combine those two, you get a complex phase. Okay, so that's kind of a quick preview. And I do want to discuss relative phase when we get to quantum bits. So I started talking about it today. I want to do it in more detail when we get to it. Okay, so that was phase. Oh yes, and then the phase is related to the entropy. It's directly related to the entropy because when we talk about quantum bits is entropy. Qubits are quantum entropy. So when we get to quantum entropy, then we have to discuss relative phase. And when we discuss relative phase, then we need to discuss complex numbers. Okay, so that was a quick aside. So where was I? Oh yes, so we were talking about how to convert information into physical work. Now I've been posting this on Facebook throughout the course of several years. Every once in a while, I'll post this. Information is a physical thing. So when I say information is physical, I'm specifically saying that you can convert information about a system into mechanical work, and then that would be like a potential energy that's becoming manifested into kinetic energy, and then that act of manifesting a potential energy, that is converting the information from thermodynamic entropy into kinetic energy. And that is sort of a brief rundown on what entropy is, and what it is definition-wise. Basically, you're using the capital Omega to count the total number of potential microstates to form a microcanonical ensemble of the microstates. So in the classical picture, you have molecules of gas with definite positions and momenta. Momentum is basically speed times times the mass with a direction. So you have mass, speed, direction, and those three combine to make a momentum of the molecule. And the molecule, if it has a momentum, then it has a kinetic energy. And then the kinetic energy can bump up against the piston, and then you convert it into work. And now, that's the classical picture. Now the quantum picture is how do we know like what position a molecule has if we never actually measured it? So if it's entropy, right? If it's entropy, then we don't actually know what the position and momentum is for a given molecule, because if it's entropy, by definition, we don't know what it is, because by definition, if I'm using the Shannon definition, oh, it's this one here. Okay. So by definition here, we do not know the microstates. These pKs, these are actually the probabilities of those microstates. And if we don't know which microstate we're in, how do we know what the position and momentums of the molecules are? So now probability is something between like 0 and 1. So like if I roll a die, like a 6-sided die, you could say, well, what's the probability of like rolling a 1, right? Well, the probability of rolling a 1 is 1 out of 6. So that's the probability of being in that microstate. Now if it's impossible to know which microstate you're in, because you have a certain amount of entropy, which is information that you don't have. If you don't know which microstate you're in, how can you say with any certainty that the molecules even have a position and momentum? So think about that. And then you can also Google search the uncertainty principle, which I'm going to be using as like a central like concept to these videos, is the uncertainty principle. And the uncertainty principle basically says that you cannot know the position and momentum of a molecule precisely. You cannot know both of those. So what that indicates is that a given molecule does not have an exact position at any given moment. if you measure the position, you have to use energy in order to actually measure the position. So like if you look at it, if you look at the position of a molecule, you have to use a photon, or you have to use light waves, and you have to bounce the light waves off of the atom, and then it comes back, and then the light wave comes back into your eye, and then that's a way of like measuring the position, right? Now when the light hits the atom and bounces, then the energy is actually going into the atom, and then you're changing the kinetic energy of the atom just by looking at it. So yeah, that's right. Yeah, and it changes the position too when you look at it. So because if you yeah, thanks Jessica, thank you. Yeah, so if you observe the position, you're giving it a random impulse, and you're introducing an uncertainty in the momentum by observing it optically. You're imparting a random impulse to the atom, which by imparting that impulse, you're also changing the position. So in other words, by observing the position of a molecule, you're changing the position of that same molecule. So in essence, in quantum mechanics, we don't really have positions. That's a lot to take in, right? So instead of positions, we actually have like a probability wave of positions. So you have a statistical model of where the positions would be if you were to measure it, and then you have here, I'll write a short, and I'm going to be getting into all of this in much more detail in the future, but basically this would be like a wave vector in position space. You have like bra x ket psi, so that would be like a position wave, and that position wave keeps track of phases also, and when you square the amplitudes that are in front of each vector, then you can get probability of being in that position if you were to measure it. But the minute you measure it, then it fucks the whole thing up, right? That the minute you measure it, then it collapses into a Dirac delta function, and then it changes the momentum completely. So that's like the quantum picture of these gas molecules. So like you can think of it classically as molecules moving around, and you'll be able to discern how an engine actually works by understanding the classical picture of entropy. You can discern it. But oh, you're interested in wave dynamics? Yeah, me too. Yeah, I'm like super into it. Okay, so the point I was trying to make with that is that the classical picture of balls of stuff moving around, it'll give you an idea of what's going on, but it doesn't give you the full quantum picture of what's going on. And at the microstate level, these molecules are quantum. So we really want, or actually, in order to understand emergent gravity, we have to understand the quantum picture of what's going on. Originally, I was trying to write my paper, my article, using classical thermodynamics, and the only reason I was doing that was because the professor was like insisting on it, and I kept telling him again and again, like, you have to use some quantum concepts, and he just wasn't hearing me. So I ended up the first time I tried to write it using purely classical thermodynamics, and then towards the end of that first draft, then he realized, oh, you know what? Okay, we do need some quantum concepts. So to really understand emergent gravity, you have to understand the thermodynamics, and you have to understand the quantum mechanics of the thermodynamics. And to do that, you need to understand the Shannon's entropy equation, which is measured in bits, like a computer. The Shannon's entropy is measured in bits. But you can convert that into thermodynamic units. All you really need is a Boltzmann's constant to do that. And we change the base of the logarithm over into e, to the natural logarithm base, mostly for the purposes of the statistical modeling, because we want to use like the exponential base e, and that, you know, oh yeah, and then that's the thing that you can study if you're still at the algebra level. You can study logarithms, so study those if you're following along at the algebra level. And what you'll see when you study logarithms is that converting the base is also a linear factor, right? Or just like a factor, just like K. Boltzmann. It's like a constant that you multiply, just like the Boltzmann constant. So it doesn't change much going from Shannon's entropy to thermodynamic entropy. It doesn't change much as far as the equation is concerned. These two are pretty much the same. The script S and the capital S, they're pretty much the same thing. Now, why does it not matter what constants you use? The constants that you use, as long as it's like a logarithm of the microstates, if it's a logarithm of the microstates, the constant that you use doesn't matter so much. And the reasoning behind that is the second law of thermodynamics. So what we've been talking about up to this point has been the first law. Now, what's the second law of thermo? So in a closed energy system, now what do you think that means? So in an open energy system, which is what I have written out here, dE, that's the change in energy. So what's happening here in the general form of the equation that I have written here, this energy system is allowed to exchange energy with other systems, and that would be exchanging energies with other systems is an open energy system. And open energy systems, they can lose entropy, right? So going back to the cup of tea analogy, when your cup is boiling and you see the steam coming out of the cup and going into the room, the cup of tea is losing entropy because it's an open system. So your entropy of the cup can go down, right? Now, why is that? Because you can actually see the heat in the tea flowing out of the tea and into the room. And when that heat flows out, the cup loses entropy, but the room gains entropy, right? The room is gaining entropy. So what the second law of thermodynamics is saying is that if you combine the two systems into one system, that's the room and the cup, then that total system would be considered a closed energy system. And basically the second law of thermodynamics says that for a closed system, the total entropy has to increase or stay the same. So now, because the cup is not in thermo-equilibrium with the room, the cup is going to lose entropy until it reaches thermo-equilibrium with the room. And then at the point that the cup reaches room temperature, when the cup reaches room temperature, then the entropy stops, right? So what happens? Well, the total entropy has reached maximum entropy. Now this is, if you're at the calculus level, you can study maximum and minimum of functions, which is going to involve differentiation. So to study that, you need to be able to follow calculus. But I would encourage you to study that if you're at that level. Optimization is very important. Optimization. So with the entropy, what the statistics is doing with the entropy is you're optimizing the entropy, and the thermodynamic system is approaching maximum entropy. Now, when you maximize a function, it doesn't care about the scale factor. It only cares about the function. So like let me just draw a quick graph here. Okay, so like here's two functions. Okay, here's two functions, and you can see a dot at the maximum, and you can think of these functions as the same, but having different scales, but they can represent the same thing if you're doing maximums, right? So if you're finding the maximum, they can be regarded as the same function, just within a scale factor. So like the short one is like, I don't know, like 2/3 of the tall one, or however much, right? So that's a rough idea of why these two entropies are exactly the same, because the scale factor determines units, but not maxima, or not so the optimization of it comes out the same regardless of the scale factor. So as far as reaching equilibrium, the two types of entropy can be regarded as equivalent. All right. So it's really just a units thing. With Shannon, you're measuring it in bits, and with thermodynamics, you're measuring it in terms of energy. Well, yeah, we can just keep it at that. We're measuring in terms of energy because the dq is measured in heat energy, right? So if you're measuring it in joules, then your Boltzmann constant would have to convert the entropy into joules, right? Which is a measure of energy. So so really it's just a matter of units in the equation, and with optimization, the units don't really matter. So with bits, it's like an information theory context, and then with the Boltzmann's constant KB, it's like a thermodynamic context. And the thing that I want to emphasize is that they're pretty much equivalent, especially when taking optimization. Okay, so any questions so far? Oh wow, I went on for a long time. 50 minutes so far. Aries, basically I've been discussing entropy, like, I just did a rundown of like what entropy is, and all of this is in the context of emergent gravity. So basically I wrote an article on emergent gravity, and then I realized that, maybe like 10 people on planet Earth can even understand the article. So then I realized that I kind of need to like break it down and like explain each concept and what it means. So I started with temperature yesterday, and then today I've been discussing entropy for 50 minutes. So you can go through and catch up on those two videos. And then I also gave you like a list of things to study throughout the videos, and I'm kind of breaking it down into multiple levels. So we have the algebra level, we have the pre-calc level, and then we have the calculus level. And then the physics stuff, you can study that. You can study the physics stuff at all different levels of math. Some statistics is essential. Some knowledge of statistics is essential, and that stats can be studied at all different levels of math as well. So okay, what else can I say? So besides, you should study Maxwell's demon. Oh yeah, gravity is just amazing, just an amazing thing. So I got obsessed with gravity. I got obsessed with gravity. I've always been kind of curious about gravity. So I wrote an article on emergent gravity, and I realized that that most people can't understand the model that I wrote. So I'm going through and I'm kind of explaining what it means. And we're starting with thermodynamics. So basically we need to explain thermodynamics in not only quantum physics territory, but we need to understand thermodynamics in an information theory perspective. And if you understand thermodynamics in an information theory perspective, then you can understand how computers are using thermodynamics. And then if you can understand that, then you can start to understand how emergent gravity works. Now the bits of entropy. So going back, we were talking about gas in a container. So the molecules are in 3 dimensions in the container, right? But if you're outside of the box, then you don't have complete information of what's going on inside the container. What you have instead is you have a statistical model of how the molecules are moving, right? And this statistical model has to take into account uncertainty, which brings you into the quantum realm. And now you can think of the entropy of the microstates of those molecules. The entropy is the information that you don't have about the molecules, and you can store them on the 2-dimensional surfaces of the container. So if you're in a cylinder, you can actually store the entropy on the 2-dimensional surface. So the entropy is the information about the microstates that you don't know, and you can store it on the 2-dimensional surfaces. So here we actually have a dimensional reduction from 3 dimensions down to 2 dimensions. Not only that, But we're talking about information entropy. Okay, so this is pretty heavy, right? So now if we go back to the the meme example, so the meme is stored as kilobytes, right, of information, and what can happen is that you can sort of imagine that you have a three-dimensional picture on a two-dimensional surface being projected as digital pixels of information. So like the video you're watching right now, this is converting a three-dimensional room. Like you can see, we have a three-dimensional room, and it's converting that information about the three dimensions. It's converting it into bits of information, and then it's storing the bits of information on a two-dimensional surface, which is your monitor, right? So it's storing that bits of information on a two-dimensional surface, and the two-dimensional surface bits are regarding a three-dimensional, like I guess manifold. Yeah, sure, like manifold. So we have a three-dimensional manifold that's getting converted into two-dimensional data. So that analogy is going to take you a long ways, and I've already gone almost a full hour talking about what entropy actually is. But understanding that dimensional reduction aspect of digital entropy is going to take you a long ways into understanding what we're talking about when we're discussing emergent gravity. Okay, so are there any last minute questions? So in the next video I may discuss qubits, like quantum states that have bits of entropy, and you can start looking into that if you wish. So that's what I'm planning for the next video. Oh, you know what I forgot? It's not that important. Okay, I'll talk about it real quick. But the script S equation here, that's the Shannon's entropy. So what I want you to do is I want you to think about how to compute the entropy of a quantum state or a quantum wave vector. I want you to think about how would I find the entropy of one of those. Now here, these two equations here, I forgot to talk about them, so I'll wrap that up real quick. These two equations here for the entropies, N and capital S, these are near thermal equilibrium, and near thermal equilibrium they have a much simpler form. Remember, capital omega is the total number of possible microstates. You have a base E logarithm. You have Boltzmann's constant, and then that would be the entropy if you're near thermal equilibrium. Now, what is this saying? It's saying that near thermal equilibrium, each microstate has the same probability weight, right? So then the model is a lot simpler to work with if you're near thermal equilibrium. Now, what this has caused for me is this has caused me to question a lot of the results and predictions from classical thermodynamics. I've come to question it because of the what we're calling the ergodic principle. This is basically an assumption that each microstate is equally likely. I don't agree that this is the case, especially since with most of the applications of thermodynamics, you're actually not you're not in thermal equilibrium. You're actually using the fact that you're not in thermal equilibrium to drive your mechanical system towards thermal equilibrium. So the ergodic principle doesn't really apply that well. Now we should kind of run some numbers and some examples and compare, well, how close does the approximation match the experimental observations? Like, how close does the approximate model match the actual model, right? So that's why I prefer to write the entropy in probabilities, because in most of the cases that I'm using this, we're actually not in thermal equilibrium. In most of the cases that you would be using these applications. Now, in the Verlinde emergent gravity model, if you make a lot of simplifying assumptions, sometimes you can regard it as thermal equilibrium. But you have to do a lot of like mental gymnastics to make that approximating assumption. If you make the approximating assumption, then you can use the thermal equilibrium model. But in most applications, I prefer to use the probability entropy equation. Okay, so that's the one thing I forgot. What if you were moving up, Jessica? What if you were moving up dimensionally? Is there math for that instead of reduction? Yes. For that, you would want to look into conformal field theory. So in conformal field theory, your manifold is in p plus q dimensions. So p dimensions of space and q dimensions of time, and that with conformal field theory, that's how you can get a higher dimensional model. Conformal field theory is good because you have local quantum field theories. So that's a lot to chew on. So I'll let you start there, and then you can ask additional questions once you look into that. So the math that you want to look into other than dimensional reduction is going to be conformal field theory, and in conformal field theory we are still concerned with a dimensional reduction into anti-de Sitter space. Anti-de Sitter space is where we are going to be concerned with quantum gravity, is anti-de Sitter space. So basically we're going to want to dimensionally reduce that in the conformal field theory. So it's still going to apply, but it's going to apply at higher dimensions, which is probably what you're thinking about with the string theory applications. Aries, have you seen what happens when you levitate water? Maybe. That does kind of ring a. Yeah. Okay, that's where you're going with it. Water tension, but space tension. Yeah, very good. Yeah. Okay. Yeah. So what I was mentioning. So what I was mentioning with Jessica's question is that what you have is you have a manifold. So the manifold that I've been working with are 3 plus 1 dimensional. So that would be the physics that you will typically observe is 3 space dimensions and 1 time dimension. So you can think of this as 4D, but we typically separate it into space / signatures and time signatures. So in a lot, like, well, especially with classical models, we'll have 3 space, 1 time in the manifold, and with time being a measurement of space, that is correct. That's correct. And I'll write you a couple of equations real quick. Okay. X0 Okay, so these are your special relativity coordinates, and these are the ones that I usually try to use. With relativity, you have lots of different choices. Now, this is the choice that I prefer, and especially with Wick transformations. The X0 term has sort of like a built-in like Wick transformation, and usually like I've seen the X0 term go as like X4 and crap like that, you know what I mean? But here, the way that I write my special relativity coordinates is the X0 term is actually a geometric measurement of time. So the c is the speed of light. The speed of light. And when you multiply meters per second times time, which is in seconds, that gives you the amount of distance that the light has moved in that amount of time. So the X0 term is measured in distance, meters. And then XYZ is your usual space coordinates, right, measured in meters. And there's lots of different ways you can write your coordinates. Your XYZ, these are your rectangular Euclidean coordinates. That's the XYZ, and that's the math that you're probably the most used to in geometry is XYZ. Now I can do other videos on why all of this geometry implies that the time is a measurement of space or movement, right? Just what you said, Aries. Now it's because the t and the XYZ coordinates are all related in the distance metric. Okay. Now, why do you think I put an I for the imaginary number? Why do you think I put an I? Well, it has to do with the signature of the manifold, first of all, and the reason I prefer the I is because aesthetically, I like to use a Euclidean metric. So in special relativity, you have to use the Lorentzian metric to measure distances. And distances in relativity involve displacement in time. So what I'm doing here, when I'm geometrizing the time unit, and I'm including an imaginary component, is with the Lorentzian metric, you have to subtract the time displacement from the space displacement. So that's through the metric is how the time coordinate is related to the space coordinates, and that's like a long way of saying that you're absolutely right. Where time is a measurement of space, right? And now the I makes it so that when you square it, it changes into a negative number. So when you square it and it changes to negative, that means that you can use Euclidean distance on complex numbers. So then you can use the same geometry that you learned in grade school, the same measure, the same measurement equation you can use that you studied in grade school, but with complex numbered time. The squaring of it makes it a negative, so it takes away from the space measurements. Now, as far as the levitating water with sound vibrations, the comment I would make on that is particles have a frequency space. So if I take my wave equation, where did I write the wave equation? Oh, here we are. Okay, so I can write my particle in position space, or I can write my particle in momentum space. In momentum, if you drop certain constants like h bar and c, if you drop out certain constants, you can actually change the momentum into frequency. So the frequency of the particle has to do with the momentum of the particle. Oh, thank you, Jessica. And we already finished covering entropy, so I'm just getting ahead of where we're going. But yeah, thanks for showing up for the entropy part. Yeah, so the particle, you can write the wave equation in momentum space, and then if you drop certain constants from the equation, like h bar, then basically you have an equivalence between momentum space and frequency space. So then when you write the particle in frequency space, then you see a direct connection between the acoustic waves that Aries mentioned. And with the acoustic waves, it's much easier to get a visual of what's going on. So I've seen certain holograms. I forget who showed me, but yeah. If this is you, feel free to comment. Whenever this video gets to you. But someone showed me that they made a hologram where they put like a balloon, like a latex balloon, on some kind of surface, and then they shine laser light through the balloon, and then what they did was they bounced certain acoustic waves at various like hertz frequencies, and they bounced these acoustic waves off the balloon, and then that changed the two-dimensional surface. And then the lasers, the optical lasers would project a three-dimensional image. So this is another really good example of the dimensional reduction, right? Because you have acoustic waves on a two-dimensional surface, and then that's projecting three-dimensional optical information. So you can get a three-dimensional visual of the two-dimensional acoustics. So three-dimensional photons from two-dimensional acoustic frequencies. So I was super impressed by that. I forget who I saw it on Facebook, and I was super impressed by that hologram. It was really cool. Okay, so I hope that answers your question. So are there any other last-minute questions or comments? If not, we already this video already went way longer than I was expecting, which is, it's cool because we got ahead quite a ways on a bunch of other topics of what we can cover, especially if people follow up with comments of things that they're interested in, things that they'd like to know more about. My plan for the next video is to cover qubits. We covered bits today. We started covering quantum bits, but we didn't get very far yet. But we started that today. So now the original 2011 version of emergent gravity, that was written using classical bits. But it occurred to me reading that the theory will only work if these bits are quantum, and it has to make an information theoretical account of entanglement, and that's the only way that the particle can observe the two-dimensional holographic projection screen in the emergent gravity model, is if the particle frequencies are becoming entangled with the entropy qubits. And that was one of my original contributions to the theory that I'm in the process of attempting to publish now. So we can follow up in detail on what that means in future videos. Thanks for tuning in. I look forward to hearing more from you. Have a good rest of your day. Oh yeah, Jessica, I can post a link of the article. Yeah, let me follow up. Yeah, so I can post the article, and don't forget that you don't have to feel like you need to understand all of it on your own. Okay, so that's the real purpose of these videos, is to explain the article in such a way. My goal is for someone with a grade school math background to be able to follow the model, and then the more math that you can do on your own, the more math that you can do on your own, the better. So I am asking you to research some of these concepts to the best of your ability, and I'm trying to make it accessible to everyone. Yeah, so I can post the link. Have a great rest of your day, and I will see you next time.